In this section, we are going to look at the chemistry of phenol. So what's in the name? Well, phenol comes from the joining of two Greek words, pheno, which basically means to shine, and ol, which basically means an alcohol. And why shine? Well, phen itself was originally used in the naming convention of benzene. And benzene came from the illuminating coal gas that they used to light up lamps and things like that. So it was a kind of alcohol that derived from the illuminating gas that was found within coal. And so that's where we get the name from. It's the addition of the two. But what is it structurally? Well, I've got 4 different representations on this slide. And they're all crude, I suppose. None of them are exactly right. Some are more right than others. So the very first one, and if you're a fan of Molyneux, which I am, this is how all of their organic compounds are displayed. And quite often that's the one I will use, even though there are obviously significant limitations of that model. It's a structural formula showing the shape and the presence of single and double bond in the ring. And as you can see, how it is incorrect is it's not showing the pi structure of the benzene ring. It's showing it as alternating double and single bonds, which we know benzene and that aromatic ring does not have. However, it does persist, and so we do see that in lots of places, and it's perhaps the easiest to get some programs to draw. We will probably use that extensively, but beware, the caveat is that's not correct. The second one shows the skeletal formula with basically the same structure. And notice how this is a benzene ring with the hydroxyl or the OH group attached to the ring. Perhaps the most accurate skeletal representation is that third one along, the one with a circle in the center of the aromatic ring to denote that delocalized electron ring above and below the plane of the hexagonal shape of the aromatic ring. And then finally, a ball and stick model, which again, Molyneux, my favorite website, it creates these ball and stick diagrams. It again has placed double and single bonds in that. Now I'm going to use a range of different things, but just be aware, it's how it's displayed. What is phenol? It is when we join alcohol functional group, the OH group, a hydroxyl group, to a benzene ring. Now you certainly will have encountered phenol-based chemicals before. You ever heard of TCP? It's a disinfectant, and it's one that's used if you scratch your arm and you want something to put on it to kill whatever microbes you might have picked up from the environment. Well, how this works is it's a phenol structure, so it's an aromatic ring with the OH group attached, and then in the 2, 4, and 6 position on that ring, we have chlorine atoms, and it forms this 2,4,6 trichlorophenol, TCP. Now, how it works is that this phenol is actually lipid soluble. When it comes into contact with a cell, and it can be any kind of cell, then what it does is it can insert itself in that phospholipid bilayer that forms the cell membrane. And in fact, disrupting the strength of the membrane, basically it gets its way in there and it ruptures the membrane, allowing all of the insides of the cell to pour out. So why do they put this on your skin? Well, your skin is covered in a dead layer of skin cells that are not going to be affected by this mechanism, whereas any germs on the surface of your skin are going to get punctured by this chemical. It's really fantastic because it basically means that we can selectively kill the germs on our skin without killing our skin cells itself. And let's have a think about how microorganisms are killed by these different chemicals. The phenol groups, well, they are going to be lipid soluble. They'll dissolve lipids. They'll basically disrupt the membrane of a microorganism. And the way that they do that is because the actual benzene part of this molecule is non-polar, whereas the OH group is a little bit polar. And so being dominated by this non-polar section of the molecule means that what it's going to be able to do is it's going to be able to dissolve fats. Whereas if it was a polar molecule, it would basically be water soluble rather than fat soluble. Now, with things like alcohols instead, what we find is it all depends on the length of the chain of the alcohol. If it's a very small alcohol, then it's dominated by the OH group. It makes it very water soluble. But if it's a long chain alcohol, it's dominated by the non-polar part of the molecule, and therefore it becomes lipid soluble, or alternatively, it's basically just going to be able to dissolve non-polar solutes and liquids. And so therefore, they have a different mechanism. What we find is the difference between disinfectant you might spray on the surface is it physically punctures the cells by breaking into those lipid layers, whereas alcohol hand gel, it works by basically dissolving the water content from those things. It's very, very small alcohol molecules that evaporate easily that actually dissolve the membranes and denature the proteins. But what about soap? Well, soap is basically it's a long chain hydrocarbon connected to a carboxylate, and it's very, very similar. It works in a very similar way. The one side is the carboxylate head is very hydrophobic, it hates the water, and the long tail is quite hydrophilic, and it likes the water. But what it physically does is it likes to physically surround any little bits of oil or fat. And so physically what it will do is it will physically start to physically surround the whole lipid layer on the outside of the microorganism, basically getting in between the microorganism and your skin. And so what soap does is it physically detaches the microorganisms from your body. That's quite clever, isn't it? Now, the phenol groups are so useful as disinfectants that we might actually see many different types of phenols used as disinfectant. Last one was TCP. What about Dettol? That's a family name. That's a very very common chemical that we'd spray on our work surfaces. It's very similar to TCP, except rather than having the three chlorine atoms, it has two of them replaced by alkyl groups, methyl in this case. But otherwise, it works exactly in the same way as TCP itself. So what do we get if we attach other things to the ring? Well, what about a carboxyl group? If we attach to the COOH, the carboxylic acid, we'd get something like this, 2-hydroxybenzoic acid, or salicylic acid is its original name. This is used in skincare products for treating things like acne. It's a precursor for making aspirin, and it's a starting material for many dyes and preservatives, so very, very useful in the chemical industry. What about the nitro groups? If we put NO2 onto the ring, then we get something like this, 2-nitrophenol. It's used as an intermediate in the manufacture of dyes, pigments, pesticides, pharmaceuticals, you name it. So when is a phenyl not a phenol? Well, okay, so phenyl with a Y is corresponding to, it's the old word for benzene, and any chemicals that are derived from benzene with things attached is perhaps called phenyl. Now, not all of them are going to be phenol. What we need for phenol is an OH group directly attached to the ring. Now, even some chemicals that do have an OH group are still not phenols if there isn't that direct attachment. Take this for an example, 2-phenylethanol. And what you can see is the ring, and then there's like a chain of carbons, and then the OH group. That makes this technically an alcohol rather than phenol. Phenol, we specifically reserve it for those situations where the OH is attached directly to the group. And so, though this is not a phenol, you still may have encountered this chemical. This sometimes the old name for it is phenylethyl alcohol. It is what creates the rose scent in ingredients of perfumes, cosmetics, flavoring agents in food, in things like Turkish delight, roses, chocolates, but also rose-flavored perfumes, eau de colognes, that sort of thing. It's even present in rose petals themselves. It's the scent of a rose. So how do we manufacture phenol in the first place? Well, the starting ingredient is, of course, benzene, which is an oil derivative. Now, there's this process called the Dow process. It was developed in the first part of the 20th century by the Dow Chemical Company in the USA. And basically, it's a multi-step process where we get our benzene and we react it with H2SO4, sulfuric acid. And what that does, it sulfonates the benzene ring. And basically what happens is we end up with the sulfur connecting directly onto one of the carbons in the ring, and it produces that little chemical that you can see there after the arrow, sodium benzene sulfonate, and some water. And now with that, what we then do is we add it to extremely hot solid sodium hydroxide. Now, sodium hydroxide solid has a melting point of about 315 degrees C, and we actually heat this up to about 300 degrees C, so it's right on the edge of its melting point. And at that point, we add the benzene, and what happens is we get fusion occurs. That's a word that we don't tend to use very much in chemistry, but basically what happens is the sulfur part disconnects from the benzene ring and is replaced by one of the oxygens, and in a very acidic environment afterwards, protonation occurs. A hydrogen will then join onto that oxygen, forming the phenol. Now it produces a yield of about 60%, and a really important detail about this is that it produces quite a lot of other chemicals along the way. It produces water, and it produces sodium sulfate, as well as producing some sodium atoms itself. So the yield is 60%. The atom economy is going to be quite low, and also it requires very high temperatures. Heating solid sodium hydroxide to 300 degrees takes energy. So the search was on to find a better and more efficient way of doing this. So a better process for making phenol, sometimes called the Hock process, but unfortunately that's named after a person that didn't necessarily discover this process first. So you'll see some books call this the cumene process. Udris and Sergeyev, two Soviet chemists in 1942, found this first, but due to secrecy and such, that work wasn't well known. But what was more well known was Heinrich Hock, the German chemist, in 1944. In somewhat difficult circumstances, was able to develop this, and so it was sometimes called the Hock process, but I will refer to it as the cumene process, just to leave the priority out. So how does it work? Well, it starts off with benzene, like all others, and what we're going to do is we're going to mix it with propene, and what is going to happen is in the presence of an acid catalyst, it is going to remove one of the hydrogens from the propene, and instead the propene is then going to attach to the benzene ring, and so this creates the chemical cumene, which is basically it's like an alkene attached to an aromatic cumene, it's called. And what we do then with this cumene is we oxidize it by basically pumping O2 through it, and it creates something called cumene hydroperoxide. Difficult to say, but basically we've now got an oxygen attached onto the alkene group that is attached to the ring. And then the final thing we do is we do something called acid catalyzed cleavage, where we basically snip that oxygen in half and everything gets reorganized around. And what happens is we have one of those oxygens remaining on the benzene ring. In an acidified situation afterwards, it will be protonated so that it then forms the OH group, and then we get the phenol. But the other thing produced, which is quite interesting, is we'll end up with a little hydrocarbon that is 3 carbons long with a double bond to an oxygen in the middle. Acetone, which you're probably used to get your nail varnish off. Acetone is a phenomenally useful chemical. It's a fantastic solvent of various different things. So this cumene process, first of all, it gives higher phenol yield compared to the Dow process, 86%, but it also only produces one waste product or side product, acetone, which is itself extremely useful. So both products have got great on-sailing ability, that you could actually sell both of the products of this, and so the whole thing is just generally much better. Also, the presence of catalysts mean it can be done at ambient temperatures, so there isn't a requirement of a huge amount of energy input to get this to work. And if we think about things like yield and atom economy, well, remembering that atom economy is the sum of the molar masses of the desired products divided by the sum of the molar masses of all the products. So like, what fraction by mass of the product is what you wanted it to be? Well, the Dow process, it's about 34% compared to 62% for the cumene process. And that's just assuming you're only after phenol. If you also said that the acetone itself was a useful product, then all of the product is desired, and all of it is therefore useful, making it 100%. Who wouldn't want that? And for that reason, the cumene process is now the process that is used industrially to produce phenols. Let's take a look at what happens if we put phenol in water. Well, when it's in water, we get actually some dissociation. That hydrogen that is hanging on to the OH group can basically get lost and go into the water. And therefore, in donating a hydrogen to solution, it is a weak acid. Now, we call it a weak acid because it only partially dissociates. Not all of the hydrogens leave. All of the rest of them that are involved in the hydrogens around the ring, they all stay. It's only that one hydrogen that can be dissociated. It's a weak acid, and so therefore we use the little backwards and forwards sign, because what we find is that that hydrogen that is lost into solution can also come back and rejoin, and how readily it does so depends upon the dissociation constant. If we have a little look at the dissociation constant for, here's three different things: ethanol, just a basic alcohol; phenol, this, and ethanoic acid, you can see that phenol is about in the middle. Now it means that it has got some power to have reaction with bases, but not as much as some other things. Ethanoic acid is a stronger weak acid. It has a much bigger dissociation constant, and so therefore it will react with strong bases like sodium hydroxide, but also weaker bases like sodium carbonate. Now, phenol is more discerning. It has a much smaller dissociation constant, meaning it doesn't give out as many hydrogens, and so therefore it would only react with a strong base, sodium hydroxide. It will not react with something that is a weak base like sodium carbonate. Now, ethanol, as an alcohol, you don't normally necessarily consider ethanol to be an acid, but indeed it is a very weak acid indeed. It's very difficult to get that hydrogen to leave, but indeed it will, but just not in any great way, and so therefore we don't see it reacting with things like sodium hydroxide or sodium carbonate. So if phenol is in solution, is technically an acid, can we neutralize it? Yes, but there's not really much use in doing so. What we could do is we could make it react with sodium hydroxide, and what would happen is the sodium would basically be attracted to the sodium ion. Once it's dissociated in the solution, will be attracted to the O- ion that is now remaining after the H+ ion has left. We would end up with a salt called sodium phenoxide that no one's interested in. So why are we even talking about this? Well, it's because these reactions help us to identify when phenol is present. Like, how do we know if we've got phenol or if we've got some other carboxylic acid like ethanoic acid or something like that? Well, this reaction, the fact that it will do this, it will neutralize with sodium hydroxide, but not with sodium carbonate, says you've got yourself a phenol just here, not something like an ethanoic acid. So the reactions that it will do are kind of diagnostic in determining, well, what is the thing that I have in front of me? I can use it forensically, if you like. So as chemists, must we be careful of phenol in the same way that we must be very careful of benzene? Well, the best advice is to not touch benzene with a barge pole. It's a very dangerous chemical indeed. It's carcinogenic, cancer-causing, especially leukemia. It's extremely volatile. It'll get into the air. It's also flammable. It's a very, very nasty chemical indeed. But phenol, strangely enough, it doesn't have those same carcinogenic properties. And so even though it still has the Has symbol for systemic organ failure, it's not systemic organ failure due to it being cancer causing. It's actually just a really terrible poison. Great. And so with the correct precautions, it is much more handleable in the laboratory. The main thing, of course, is it's a corrosive poison that gets in through your skin. And so it's there's less of an inhalation risk because it basically can be solid at room temperature. It's less volatile, but acutely damaging on contact, which means full covering of all of the skin. So what causes this difference in the reactivity between the two? Well, for benzene, not for benzene, for the phenol, a lone pair of electrons from the oxygen p orbital of the OH group get donated to the pi system. And this increases the electron density of the pi system, which attract electrophiles more readily. Those chemicals that are interested in electrons will find more in a smaller space in phenol than in benzene, and that brings about its enhanced reactivity. Now that means that phenol will undergo most of the same reactions that benzene will, except phenol goes into it with much more enthusiasm, being more reactive. It means that we can get it to react under much milder conditions. So if we remember those electrophilic substitution reactions of benzene, well, they can also happen with phenol as well. So for example, bromination, where basically we have some bromine water in this case, and we slosh it around with phenol, and what happens is the bromine will split up, and you get 3 of those bromine atoms attaching in the 2, 4, and 6 position on your phenol, and you get hydrogen bromide left over. And so there it is, it forms 2,4,6 tribromophenol. And the greater electron density of the pi system polarizes the bromine, so unlike with benzene, no catalyst is needed. If you remember, all of those electrophilic substitution reactions of benzene required a catalyst to be present to polarize the molecules in the first place before they could be attracted to the electrophile. Here, the enhanced electrophilic properties of having those extra electrons in the system does it all for you. Now, if you were physically to do this, what would it look like? Well, I've got some phenol just there. It's solid at room temperature. And I've got some bromine water. And when you add one to the other, the first thing that you notice is that the bromine water decolors. It goes from being an orangey brown to being clear. The second thing that happens is a white precipitate forms, that this 2,4,6 tribromophenol is a solid and so appears hanging in the liquid there. The only thing to remember is the decolorization of bromine water is the test for an alkene. So you've got to be careful if you were presented with the results of certain tests in this particular chemical, decolorized bromine water, you'd be very interested to know whether or not a white precipitate formed, because that is the difference. A phenol will produce a white precipitate, whereas an alkene will not. It will just decolorize it. So what about nitro groups? Well, if we react phenol with nitric acid, then the reaction is going to take place. What's going to happen is we're going to get a mixture formed, which is basically 2 different isomers of nitrophenol mixed together. 2 nitrophenol and 4 nitrophenol. And the only difference is that nitro group is attached in either the 2 or the 4. Does it really matter where it's attached? Well, subtly, yes. The 2 nitrophenol is attached directly next to the OH group, and that changes its properties compared to when it's attached opposite the OH group. Now, these chemicals, they are very, very useful to us. They're intermediate stages for dyes, pharmaceuticals, and explosives, but we have to be very careful because these, like those other chemicals, are poisonous and readily absorbed through the skin.